I'm going to continue now with part 4. In part 4, we had to compare the performance of two neural networks, one from the CIFAR 10 dataset, which we built and trained in part 3, with the neural network we trained with MINT's dataset in homework 4. I saved the accuracy levels, the 50 data points obtained from the training process from both of these models into a CSV file to do the comparison. And here you can see these are all the 50 data points from both the models. I have 3 columns in this data set. The first one is the accuracies from the CIFAR 10 data set. The second is the step for each accuracy level. And the third is the accuracy from the MIST data set from homework 4. So I did a comparison between both these two. I have a plot here which shows the progress of accuracy levels in both of these models. This blue line shows the accuracy levels from CIFAR 10 dataset, and the orange line shows the accuracy levels from the MIST dataset. By seeing the plot, we can clearly tell that the MIST dataset did a lot better than the CIFAR 10 dataset. The accuracy level at the end of the training in MIST dataset was almost 99%, whereas in CIFAR 10 dataset it was 67%. So there is a significant difference between both the accuracy levels. According to me, the main reason, although the structure of both the neural networks was same, still there is a huge difference between performance. In my opinion, this difference is mainly because the MIST dataset consists of images having grayscale, whereas the CIFAR 10 dataset consists images of colored uh, uh, with colored images, and so it can be difficult for a neural network to learn and extract features from a grayscale image, uh, from a colored image as compared to a grayscale image. And it might be a lot simple uh, for the neural network to extract features from the grayscale image. And then the other reason can also be that the MIST dataset consists of alphabets, so which can have a lot less properties which a neural network has to consider as compared to the CIFAR 10 dataset, which has images of many different kinds of objects. If I give you an example, uh, one of the classes is aeroplane. So there can be a lot of different properties of aeroplane and much more as compared to a single alphabet, let's say A. So uh, that is why I think uh, it can be difficult for a neural network to learn from uh, the images in CIFAR 10 dataset, which is why I think it performed better with the MIST dataset. So keeping this in mind, since the CIFAR 10 dataset did not do very well, uh, in part 5, we had to uh, improve the performance of the network, uh, which had less performance between these two. So I decided to redesign the neural network with CIFAR 10 dataset in part 5. First of all, I kept the design same and changed the number of steps in training from 5,000 to 10,000 to see if I could get any improvement in terms of accuracy. But unfortunately, there was no such significant change. So then I decided to add one more convolution layer in my neural network to see if I'm able to improve the performance of the network. And I have the critical information here for this neural network. Most of it is pretty much the same as part 3. The difference is the extra convolution layer, and hence when the data goes into the convolution layer 3 and comes out of the pooling layer 3, now the output shape is 4 by 4 by 128 as compared to 8 by 8 by 64, which was before in part 3. And then that was fed into the fully connected layer. Now the fully connected layer input will be 4 by 4 by 128. And the rest of the information is pretty much the same as part 3. And although I did not see any significant improvement in terms of uh, accuracy level, I would say relatively significant improvement, but I did see some improvement by adding this convolution layer. So the accuracy level at the end of the training process now was 68.19%. And this wasn't the highest accuracy level throughout the training process. The highest was 69.4%, which was after 3,700 steps of training. And as I said before, that this improvement is not relatively significant, but still it's a 1% improvement as compared to part 3. And if we see it in another view, then this 1% is basically almost 600 values of the total 60,000 values in the data set. So which means that this model will predict 600 more values correctly as compared to part 3. So in my view, still this is some improvement. That's it for part 5. And basically this project highlighted the properties of convolution neural networks and how they work and how we can modify some of its characteristics to make it perform better, for it to extract features from an image and learn from these features and to make better predictions. I hope you guys enjoyed my presentation and you guys learned something from it. If you guys have any questions or any opinions regarding my presentation, please reach to me directly. Thank you so much.